Okay, so hello everyone, I'm Josh Sowerby, and in this talk I'm going to give a walkthrough of Neural Frame Rate Upscaling, or NFRU for short. So this is a neural graphics technique that we've been developing at ARM, and I'm going to cover why frame rate upscaling is useful on mobile, how the NFRU algorithm works, and what resources are available if you want to explore or build on this further. So, neural graphics on mobile. What do we mean when we say neural graphics on mobile? Well, the basic idea here for us at the moment is relatively simple. Rather than rendering every pixel or frame for full cost, instead we do less work up front. So we might choose to render fewer pixels, render fewer frames, and then use a neural model to reconstruct what is missing. And here we're aiming for a high quality output at either a target resolution or a target frame rate. And in our approaches, we're not aiming to hallucinate or guess what the output is, rather reconstruct it from some input data and then use ML to replace heuristics, which traditionally might have been hard to get right. So the idea is we're trading expensive rendering for learned reconstruction. And this is particularly useful on mobile, where we have a kind of more limited power and compute budgets. And it's something we've been working on for a fair while now at ARM, and the aim of which is to make neural graphics practical on mobile. So I'm just going to quickly summarize the different kind of tools, technologies, techniques that are available to help developers put neural technology into practice. So to start with, we have neural graphics models. So these are our reference implementations, and here we have our shaders and the model weights for real-time graphics use cases. Then we have the model gym. So this covers the training side. And here we have PyTorch implementations of the models, which you can kind of use to train, retrain, fine-tune, quantize the neural graphics models that we have available. And then also we have dataset capture tools. So these are Unreal Engine plugins, which can help you capture datasets ready for training in the model gym. If you don't want to play around with retraining or modifying the models, you can just use the ARM NG SDK and associated plugins. So these contain runtime implementations of the algorithms, and additionally some Unreal Engine plugins for quicker integration. If you want to go a level below that, we have the ML SDK for Vulkan, and this enables efficient machine learning workloads to be run directly within a Vulkan graphics pipeline. Beneath all of this, we have Neural Accelerators. So this is dedicated ML capability in the GPU, well suited to running graphics and ML workloads nice and efficiently. And devices will be available soon. So this kind of summarizes kind of the whole ecosystem of what's available right now, but let's kind of dig into what the models look like themselves. So today we have three main neural graphics use cases. The first is NSS, or neural supersampling. So here we render fewer pixels and reconstruct a higher resolution output. It's effectively a drop-in replacement for TAA, TAAU. And this enables power savings whilst delivering high quality resolution for visuals. And this was announced at SIGGRAPH last year. My colleague Liam gave quite a good talk on it. And the model weights, training code, dataset capture tooling is all available today if you want to have a play around with this. Secondly, we have NSSD, or neural supersampling and denoising. And this is where we additionally added ray trace denoising to NSS neural supersampling. So this combines the supersampling and denoising into one combined step, and you'll be able to play around with this in the upcoming release of Neural Dawn, which is a game that we are releasing in collaboration with our partners at Sumo Digital, and it should be a really exciting demonstration of these technologies. And then finally, NFRU, or Neural Frame Rate Upscaling. So this generates an interpolated frame, enabling more frames to be generated at a lower cost than rendering everything at kind of full resolution renders. And this will be the topic of today's walkthrough and technical deep dive. So what is neural frame rate upscaling? So the basic idea of this is to generate a plausible intermediate frame between two frames we've actually rendered. So in this example, we render frame t-1 and t+1, and we reconstruct the frame in the middle. And there are four main things that I'm going to cover today. The first is why is this useful? Why does it help? How does it increase frame rate? How does it make motion appear smoother without paying the cost of fully rendering every frame? The second is where it fits. Frame rate upsampling is a temporal technique, so I'll explain how it can be used alongside spatial upscaling. And then third, and this will be the bulk of the presentation, I'll give a high-level overview of how it works. We'll look at the algorithm, we'll talk about the different types of motion signals that are available, and then how our algorithm actually composes and makes the final interpolated frame. And then finally, I'll touch on all the resources that are available for developers to start using it. So we've got tools, various integrations, and I'll touch on what's available today for you to go and play with. So that's what we're going to look at, and let's start with the problem that we're trying to solve with NFRU. So a total workload of like a graphics pipeline is at the very basic level comprised of two things. The first thing is how expensive each frame is and how many frames we're going to need. And both of these are going up. The per frame cost is increasing. Frames are becoming more expensive. People are using more advanced lighting techniques, ray tracing, complex materials, particles, fancy post-processing, you name it. Per frame cost is increasing as we want to do more and more. But additionally, we're also being asked to produce many more of them. High refresh rate displays are now more common, and fast-moving games benefit from high frame rates. However, the problem is that our mobile power budget is still limited, and so we need to deliver more complex frames more often while keeping within a mobile power budget. So let's say we wanted to reduce some of this rendering workload by using a technique like NSS or NFRU. To choose the right approach, we first need to understand what exactly makes up this workload. And at the high level, each workload can be split into geometry and shading. So you can see here the total cost is basically equal to geometry and shading work. If you were to employ something like spatial upscaling, like NSS, this reduces the shading cost as you render at a lower resolution. If the workload is mostly shading, this gives us quite a good saving. However, the geometry still needs to be processed. Reducing the render resolution does not change the amount of geometry to be processed, so for a geometry-bound workload like this one, reducing the render resolution and using spatial upscaling will be less impactful. And this is where frame interpolation can help. Rather than by reducing only the shading cost within a frame, we actually generate new frames, and so this reduces the number of frames that we need to render fully to achieve a high frame rate. So in summary, we can kind of reduce the workload in two different ways to achieve some power savings, in space or in time. So we've got spatial scaling, NSS, render frame at a low resolution, reconstruct missing details. This reduces the shading cost per frame, but we still need to process the geometry and render the same number of frames, and that is what neural supersampling does. Temporal scaling, on the other hand, we actually just reduce the number of fully rendered frames and we generate these intermediate frames at a lower cost. So the complexity of each individually rendered frame can stay the same. The total workload for the target frame rate will decrease versus rendering every single frame natively. And this will be the topic of today's deep dive. So let's talk about like the challenges associated with this. Generating the intermediate frame might be harder than it first appears. To start with, you might have incomplete motion between frames. Game motion vectors mainly describe geometry. They don't fully capture particles, shadows, reflections, and so we don't have a complete picture of how every pixel moves in a scene. Additionally, there's not a single correct answer when doing frame interpolation. There may be several plausible versions of the middle frame, and we don't have a simple kind of pixel perfect ground truth. And this makes training a little bit ill-defined. You don't always know exactly when you've got the correct looking output frame, even though it could still look quite good. And so, yeah, this is one of the main challenges for NFRU, although sometimes we can use this point to our advantage as well. And then simple interpolation, simple warping can produce artifacts. So if you just do a blend of some frames, you get some ghosting and disocclusion artifacts. And if you do a quite simple motion vector warp, you'll end up with some holes in the frame, and that will look quite bad as well. And this is especially difficult when previously hidden areas become visible. So the key point is that we need more than a simple blend or warp. We need a way to combine the available information and handle what's missing, and that brings us to NFRU. And this is our hybrid graphics and machine learning approach to generating that intermediate frame. So, introducing NFRU. So this is the basic idea behind NFRU. We render one frame normally, and then generate the interpolated frame between. And then we repeat, so rendered, generated, and so on and so forth. And so this gives us more frames to be presented to the user and much smoother looking motion. And you can do this without fully rendering every displayed frame, and instead pay the lower cost of frame generation instead of the more expensive full render. This additionally adds half a frame delay of latency, but overall we find that the quality is improved by the improvement in the perceived frame rate. And then this is designed for mobile, so mobile has a more constrained operating environment than desktop, and this makes frame interpolation actually even more attractive in this case. And the NFRU model that we have designed is designed to be efficient enough to work within these mobile power and thermal limits to provide power savings and cheaper frames on mobile. So what does it look like? So you have your rendered frame t-1, and then this is a generated frame at t, and then this will be your other rendered frame at t+1. So the inputs here are the t-1 and the t+1 frame, and the output is the generated frame at t. So to start with, let's talk about what goes into and comes out of NFRU and how that fits within the pipeline. So to start with, a frame is rendered and produces the usual textures like color, depth, and motion vectors. Then the next frame is rendered, producing the equivalent textures. Now for every frame pair, we can calculate the optical flow texture and then run NFRU to generate a whole new frame in between. And so the network here can generalize the selection heuristics, ensuring the most informed decision is made when producing the interpolated frames. And under the hood, we are using our Neural Accelerator, which accelerates the inference and is key to doing this work efficiently. So now let's start to look a little bit deeper into NFRU, and the first thing we're going to talk about now is motion signals, because the quality of the generated frame depends heavily upon getting the motion right. Quite simply, frame interpolation is a motion problem. To generate the interpolated frame, we need a good estimate of where the content is moving between the two rendered frames. And this matters because the intermediate pixels depend on how the objects and surfaces move between the two rendered frames, and a small motion error can turn into a very large visible artifact in the generated frame. Additionally, we have kind of newly revealed or disoccluded regions that can appear, and these need to be resolved correctly. And effectively, the quality ceiling for frame generation is set by the quality of the motion information that we have available and the ways in which we combine it. So in this example, the truck is moving forwards through the world. The camera is following the truck, so in screen space the truck appears almost stationary. And you can tell this by looking at the motion vectors on the truck, they're kind of like zero. The road behaves a little bit differently. As the camera moves forward, the road moves backwards towards the edges of the frame and towards us, the viewers. And then another interesting area to look at is the shadow. So the shadow follows the truck. It's additionally stationary in screen space, but the road is actually moving beneath it. So the kind of ideal motion is zero, but maybe not. And together, this shows why defining the correct motion can be challenging, as with different scenarios, you kind of get different types of motion, and it could kind of change quite a lot, and that makes defining what accurate motion is challenging. In NFRU, we use two different types of motion, each for its own kind of reasons and pros and cons. So to start with, we have motion vectors. So these come directly from the game's geometry. They're precise, efficient, and generally available in the rendering pipeline. But they miss motion that is not directly tied to geometry. So particles, shadows, reflections, these are not covered by motion vectors. And you can see in this example here, the motion vectors for the shadow are all pointing as if it has the motion of the road, so towards, whereas actually they're kind of more stationary. Optical flow, this is a little bit different. It estimates dense per pixel motion from the appearance between two frames. So it kind of just uses the color frames and estimates motion based on those. So because it's using just the appearance, it captures motion that geometry does not describe. So it will capture things like shadows and particles. However, it is an estimate. So it can be noisy. It can sometimes be impacted by some crazy post-processing techniques. And so it tends to be a little noisier, even though it captures some of the appearance-based motion better. And so we use both in NFRU. So motion vectors give us reliable geometry information, whereas optical flow is good for capturing appearance-level motion. And combined together in the correct way, you can take the advantages of each motion field to ensure that you capture motion effectively between frames. So what do we do in terms of optical flow? Well, for optical flow, we use ARM's block matching approach, which is designed to run in real time on mobile. So for this, we take two neighboring rendered frames, and the optical flow algorithm compares the regions of the image, sees how they move, and computes optical flow vectors. And the result of this is a dense motion estimate across the image. And this gives us appearance-based motion, capturing shadows, particle effects, and other dynamic objects that might not typically be captured by geometry-derived motion. The implementation of optical flow is optimized for real-time execution. ARM's motion engine provides hardware acceleration for this stage, so it's nice and performant and quick, and it gives us the extra motion coverage that we need to kind of fill the gaps that motion vectors miss. So this is an example to try and bring this into life, and shows a little bit about why we can't rely on geometry-derived motion alone. So on the left, this is like an interpolation run through NFRU using only geometry-derived motion, so motion vectors. You can see they describe the geometry well, but don't capture the shadow, and the result is a very kind of flickering, beating artifact on the shadow when compared with the ground truth. And so optical flow will give us this additional appearance-based motion information, including this motion from shadows, and enables us to become much closer to the ground truth. So key point is that the two motion sources are complementary, and NFRU needs both, and it needs to choose the correct ones at the correct times in order to generate a nice and reliable interpolated frame. So up until now, we've looked at the different motion signals available to NFRU and why both are needed, but let's look at like the actual system design, look at how NFRU uses these signals to reconstruct the intermediate frame. So this is the full NFRU pipeline at a glance. So I'll quickly run through this at high level before we look more at the individual stages. So to start with, we take our two neighboring RGB frames and we construct our candidate frames. So we do this by using optical flow and motion vectors to warp each of the frames towards the intermediate time step. And this will produce four possible versions of the intermediate frame, which we call candidate frames. Once we have the candidates, the question is, how should they be composed? The network uses the candidates and a little bit more context to predict blending coefficients, and these describe how much each candidate should contribute to the final frame. And then finally, we apply these coefficients to the candidate frames to produce the final RGB image. I guess one thing to note here is that the motion vectors are not optical flow are not blended together directly. They are instead used separately to construct the four different candidates, and the blend happens later on RGB. And so the aim here is that we have this kind of hybrid graphics and an ML pipeline where we use the neural network for heuristics and then graphics operations elsewhere. So what is the pre-process? We'll start to kind of go deeper into that now. So the pre-process prepares two things. So the first thing it prepares is the candidate frames. So these are possible reconstructions of the interpolated frame. They're basically different versions of a possible interpolation, and we use either the motion vectors or the optical flow on both the previous and the next frame to generate four possible candidate frames. We additionally give the network some context, some extra hints to the network about the reliability of each candidate frame. So now let's talk a little bit about how we generate the 4 candidate frames. So first we take frames RGB T of -1 and T plus 1, so these are the 2 sides of our interpolation, and we warp them with the optical flow. So we warp both with the optical flow to generate 2 candidate frames. So for example here we take RGB T -1, warp with the optical flow to T, and that generates this frame here. And we do the same with T plus 1, we warp it with the optical flow to T, and this generates this candidate frame here. Then we do exactly the same thing but using the motion vectors, warping T -1 and T plus 1 to T using the motion vectors. And by warping both T -1 and T plus 1, we create candidates with the most amount of information possible. For example, disclusions in candidate frames warped from T -1 could be resolved with a candidate frame warped from T plus 1. So this is what our 4 candidate frames are, and this is kind of how we get them. And each one of these is a possible reconstruction of the interpolated frame at T. And these are constructed in the pre-process phase of NFRU before we start trying to do any sort of neural learned composition. So I guess one thing I've kind of spoken about and not gone into too much details is the warping and what do we mean when we say warping. So I'll do a little bit of a explainer here about how we actually construct a candidate and how this is done. And we will take the generation of RGB of T plus 1 warped to T with the motion vectors as our running example. So first, let's talk about a very straightforward approach you might start with. So given motion vectors, depth and color, you can scatter the source color directly into the middle frame. So what is a scatter? What do I mean when I say a scatter? So here we use the motion to push each source pixel towards its expected position in time t, and we iterate over all of the source color and use the motion vectors at every single pixel location to push the color to the intermediate time step t. So one thing that you can get when doing a scatter is collisions. This is where 2 pixels write to the same location, and in this implementation we would use depth to resolve these collisions. So we would just take the pixel that has the nearest source depth. And so the result of this scatter operation is your candidate frame. You have moved RGB of T minus 1 with the motion vectors to T. However, this is maybe not ideal. There's a few kind of reasons. The first is that with this just naive scatter, you have to operate at full color resolution. So you have to move full high resolution color from T minus 1 to T. If you do it at low resolution, you just start to lose your nice high res detail. And so this means it can be relatively expensive. Additionally, when we get these collisions where multiple pixels write to the same position, we need to use expensive atomic operations to resolve this. So we're doing full resolution. Atomic operation scatter means that it can be quite expensive. And then the other issue we have with a scatter is that some positions will receive nothing. So this leaves holes. You can kind of see a few in this little scatter image here. You can see a line of holes. And these will need to be filled in RGB in order to ensure the image quality of the candidate frame is good. And this can work. It's not a bad approach, but it puts a lot of cost and cleanup into the pipeline. And we're designing for mobile devices, and we will want to keep this pre-process stage as lightweight as possible. So our approach changes what we scatter. We still do a scatter, but instead we scatter the motion information first rather than scattering the full color image. So the aim here is to scatter the motion by itself, and then we will do a gather of the color with the scatter motion later. This will make more sense in a minute. The reason for this is that we can scatter at a reduced resolution before gathering color at a higher resolution, which saves on cost. So step 1 is that we scatter the motion with itself. So this is the same operation as the scatter color, but rather than scattering color pixels, we just scatter the values of the motion vectors. Similarly to RGB, this is an atomic operation, and collisions are also resolved by taking the nearest depth. This results in the scatter motion texture that you can see on the right here, which is motion scattered to T. However, this can still result in holes. The scatter operation just inherently results in holes when you don't have information for every pixel. But we fill this by applying a relatively small 3x3 dilation, where we apply a filter across the entire image to take the motion from the nearest depth. And this gives us a dense, hole-filled texture at T, and typically it fills most of the holes we see from scattering, and especially if we run this at a reduced resolution, it makes your filter effectively a bit bigger, so we see most holes are resolved with this fill stage. And the aim here is to kind of clean up and remove the holes kind of quite quickly and cheaply. So once the motion field has been scattered and filled, we then gather the color. So a gather is a little bit different to a scatter. So for a gather, we actually iterate over the motion vectors at T that we've scattered and filled. And for each pixel, we read the motion vector and then we sample the RGB color from the corresponding location. And so we repeat this across the image to build the candidate frame. Gathers are much cheaper. You don't need to do an atomic. It's effectively just a texture sample, which makes use of hardware acceleration, which means that it's much cheaper, and we can do this at full resolution without it costing too much. And these three steps, scatter motion, hole fill, gather color, result in our candidate frame, which again is a frame warped and aligned to the intermediate time step. So why do we do this? I've mentioned a couple of times, but let's dig more into exactly why we do the scatter motion and gather color. Scatters are relatively expensive. If you're doing a naive scatter of RGB, you have to do the scatter stage and you have to do the fill color stage, all at the same resolution as your input and output color in order to preserve detail. However, with the scatter-gather approach, we scatter the motion at a reduced resolution compared to RGB, and then we gather the color later at a higher resolution. And so this allows us to decouple the scatter resolution from the output resolution, and that means we can have a kind of quite nice performance improvement without a drop in image quality, as we're still gathering the correct color. So to summarize the approach, T-1 and T+1 are warped with the scattered optical flow to create two optical flow candidate frames at T. And then we do the same for the motion vectors. T-1 and T+1 are gathered with the scattered motion vectors to create two motion vector warped frames at T. And we do this for both T+1 and T-1 in order to give information about regions that would have been discluded in the other frame. So in summary, that's effectively how we use scatter-gather to create our four candidate frames here. So the other thing our pre-process stage does is we generate some context. So while the candidates show possible interpolation results, they do not provide information about which candidate to trust. And we can use depth and motion information that's already available from the renderer to devise masks and confidence hints in a lightweight pre-process shader. So we basically use some extra information to create hints that we feed to the network to help provide some extra guidance. So the network will receive these four candidate frames plus this additional context to describe where each candidate may or may not be reliable. The reason we do this is that if we can find a way to give the network good hints, we find it becomes easier to instill the right behavior into our neural network, and often it means as well we can use a slightly smaller network as well, because we're feeding the network doesn't have to learn as much context. It can actually just infer from inputs we're already giving it. Also, the reason why we give the network these and not use these hints kind of directly in a heuristic is that sometimes the hints can also be unreliable as well, and so the network can choose to ignore them at times when it thinks that they are providing some unreliable information. So the first bit of kind of useful context that we might give is a disocclusion mask, and this shows parts of the candidate frame that are invalid due to disocclusions. We only do this for motion vectors, because not optical flow candidate frames, because motion vectors relate to geometry and therefore are aligned with the depth of motion anyway. So, how do we build the disocclusion mask? First, we take the depth from t-1 and t+1 and warp to t using the scatter-gathered motion vectors, and we then compare the resulting depths. We use the camera parameters to let the shader compare depths in view space rather than in raw depth buffer space, where values are nonlinear and hard to compare directly. And what a kind of large difference will tell us, it will tell us that the source frame did not contain valid information for that region, and that maybe it wasn't visible in the previous frame and it was actually hidden. And this will hint to the network that a candidate is less reliable in that region. Sometimes neither of the candidates built using motion vectors will contain reliable information for a region in our target frame, and we refer to these areas as kind of double disocclusions, and we like to provide these as a hint to the network as well. First, we build hole maps by scattering the rendered motion vectors towards t-1 and the target frame t. We then gather the t-1 hole map back to t, and then we compare the two. This gives us an approximation of where both motion vector candidates may be unreliable. In these regions, the mask tells the network not to rely too heavily on either motion vector candidate. The network can then favour optical flow candidates where they produce better information, and we found this is more robust than simply forcing an optical flow result, as the optical flow can also sometimes be a bit noisy. So, as with the other context input, the disocclusion mask, this mask is a hint rather than a hard decision, and we leave the network to determine the final blend. So that is the kind of end of the pre-processing, and at this point we will have our 4 motion aligned candidate frames plus some extra contacts that helps the network decide what to use. So now we want to ask your neural network how to solve the problem and how do we combine the different candidate frames. So the network aims to work out which candidate is most reliable for each part of the image, and it predicts a set of low resolution coefficients rather than a finished RGB image. And those coefficients describe how strongly each candidate should contribute to the final interpolated frame. And here we're asking the model to learn some heuristics, like when to trust motion vectors, when to trust optical flow, when to trust the forward frame, when to trust the previous frame, in order to create a nice interpolation result. So this is like our neural network architecture, and if you take a step back, the problem starts to look a little bit like local kind of feature segmentation. We want to select different candidates in different regions using alpha values, and so because of this, our model is inspired by segmentation techniques. So we have our encoder, and this compresses the input candidates and context into a smaller feature representation, and we additionally have a skip connection to preserve useful detail later in the decoder. The bulk of the decision making happens in our multiscale bottleneck, so this will look at the features with different perceptive fields, so small kernels will look at kind of local detail and larger kernels will look at wider scene context. And then we fuse these different views before going into the decoding stage. The decoder will convert these features into our 4 learn output channels, and these are basically our parameters that are used to blend the 4 candidate frames. The model is quantized to intake, runs at a fixed low resolution on ARM and X, so in doing this we can achieve quite good decision making capacity and run in real time. So now we have our coefficients. How do we blend them? This is actually relatively straightforward. It's just a per pixel weighted blend of the 4 motion aligned candidates using the alpha values that we have predicted. So the network's job here is to produce coefficients that A, select optical flow when motion vector warp frames are not that reliable, so shadows, particle effects, etc. And B, we want to ensure that disoccluded regions are resolved nicely by selecting from either the t-1 or the t+1 frame respectively. And in this way, we kind of learn heuristics that would otherwise be quite challenging to create with a simple algorithm. So that is a summary of the approach, and I'm going to put it all together. We have 3 kind of practical steps. The first step is constructing motion line candidates, where we scatter motion, fill the holes, gather the colour. We ask the network to predict blending coefficients and make decisions on what to use. And then finally, we compose the final frame by blending the candidates into our final interpolated frame. And it's a hybrid approach. Graphics constructs the candidate images, and the learnt composition handles decision making and heuristics. So now I'd like to talk a little bit about how we have designed an NFRU for mobile deployment. I'll just touch on a few of the little features that we have that ensure that this runs efficiently at real time on a mobile device. So to start with, we run a quantized neural network. We quantize it to int8 for a couple of reasons. The main one being that this reduces memory bandwidth, and it also can achieve max throughput on ARM-NX. However, something to note is that color information is not actually processed by the network, as we kind of showed with the system overview a minute ago. And this means that we can support high precision color if required. So the candidate frames kind of always remain in floating point color data in the same precision that they come in at, and the network does not generate or process the RGB color directly. Instead, it only predicts coefficients, and these are predicted at int8. And this means that the color information stays at full precision, and quantization impacts only the blending decision rather than the color itself. So if the prediction is slightly wrong, which can happen, the result is still a blend of real image data. You don't tend to get any funky CNN-like artifacts that you can arise when doing direct prediction, and we find the failure mode is much more graceful. So in conclusion, we can get most of the performance benefit of int8 inference while still keeping the final color path in floating point. The second part of the mobile design is we keep most of the pipeline at a fixed, lower internal resolution. So the motion processing, the network pre-process, and the inference all run at the same fixed internal size, and this keeps the cost of these stages predictable rather than allowing it to grow with the render resolution. And this means that only the final post-process runs at output resolution, so that is the gather and the composition step. This only runs at full res. So if we were to increase the input and therefore output resolution, the internal motion processing, network, etc. stages remain the same size, and you can see only the gather scales with the target resolution. And this means that we keep the more expensive pre-processing and network cost fixed across different display resolutions, and it means we can generally support quite high display resolutions without incurring a massive performance cost. Obviously it does add some cost if you run at a high resolution, because you have to do this gather at the high resolution, but it does not make the actual kind of pre-process and network itself more expensive. And additionally, most of the resolution dependent work is handled relatively cheaply by a gather and compose step. The final thing I want to touch on about mobile deployment is something that we call the compute sandwich. So this is kind of how we separate our work with the ARM-NX. So this slide kind of brings together the mobile design choices into something that we call a compute sandwich. So on the left, we have our shader core, which handles graphics native work. So motion processing, candidate frame construction, generating the context, all of that stuff is all done in shader cores. And these are operations that map naturally quite well to graphics hardware. The prepared candidates are then passed to the Neural Accelerator, and the network focuses on narrow decision-making problems, which is predicting the blending coefficients. The result is then returned to the shader core, and the post-process does the gather and the final frame construction. And so what we do is we ensure that each part of the workload runs on the hardware that best suits it. Graphics operations run on shader cores, and the NX handles learnt composition. So the neural network is deliberately sandwiched between two graphic stages. The shaders construct the candidates, and the NX decides how to combine them, and then the shaders produce the final frame. So now we know a little bit more about how the network is designed. The next question is, how do we train the thing? What's the training strategy? How do we actually make the network learn the right decisions? So to train frame interpolation, we need the two input frames and then the real kind of ground truth frame that occur between them. And so we do this by running two deterministic captures of the same content. So we capture once at 60 and then once again at 30. And because each capture is deterministic, the frames and the camera motion remain aligned between the captures. And each pass provides slightly different things. So for the 60 FPS pass, we capture color, depth, and camera metadata at every time step, whereas the 30 FPS pass gives motion vectors, and they're produced at this lower render rate. And the reason for doing this is so that we can interleave the data correctly to perform a frame interpolation triplet. So we will use the color and depth at t equals 0 and t equals 2 as the neighboring inputs, and then we'll use the 60 FPS color at t equals, the 60 FPS color at t equals 1 as the ground truth. Additionally, we use the motion data that is available for that pair captured at 30, and this needs to be captured at 30 in order to accurately reflect the motion between the color and depth frames at frames t equals 0 and t equals 2. So as you can see, this is 30, so this motion vector here represents motion between time step 0 and 2, and that kind of, by doing this interleaving between these different frame captures, we create this frame interpolation triplet, and this corresponds to a real runtime environment. Additionally, we train on 30 to 60. You could train on other kind of different pass variants, but the reason we do this is this provides a quite challenging case for frame interpolation. There is a kind of larger relative motion between the frames at lower frame rates, and therefore interpolation is much more challenging. If you were to target another frame rate, such as 60 to 20, the task would become slightly easier and NFRU would become slightly better. So the training setup that we use when we train this model is designed to match deployment as much as possible, and we have a few steps to achieve this. So to start with, we have quantization-aware training. So here we fine-tune our FP32 train model with intake behavior that we would expect to see at inference time. And so for this we use executorch, and this is included as a fine-tuning step after our main training loop. And we do this just to reduce quality drop when moving from floating point to the deployed model. It doesn't take as long as like a full training run. We do it for a handful of epochs, and we find this can recover the accuracy to pretty much the same as FP32. We also employ a robust data augmentation system. We vary color, like tone mapping and post-processing techniques, so the model is not tied to one game pipeline. And we also add particle-like effects during training. The reason for this is that we found it was more complex to capture lots and lots of particles, and it was something that the model needs to see lots of in order to do the correct interpolation for particle-like effects. So we add this kind of screen space particle effect augmentation where we kind of basically render little bits of confetti onto a frame. And we found that this augmentation helps to improve the performance of the model for this scenario. In terms of training, we use a L1 and LPIPS loss for combined spatial and perceptual optimization, and then fairly standard Adam optimization and with kind of warm-up and cosine and learning rate schedules. And we found that by doing this, we can achieve predictable and stable convergence towards good candidate selection. And then finally, we use kind of deployment-aligned kernels. So we write our pre-processing and post-processing stages as kind of shader-style slang, and these compile down to CUDA, so we get good training speed up when doing so. And the reason for this is that we keep training logic kind of quite close to GLSL that we use at deployment. We actually write our pre-processing and post-processing stages in a shader language, which keep things much more aligned with what we're actually going to be deploying later down the line. And so the common theme of these is to expose the model to kind of deployment constraints during training and development so that there are fewer surprises when we actually reach the device. And then in terms of our training data set, so the final dataset is split into roughly 16,000 frames, with 7,000 for test and 4,000 for validation. And we found that dataset diversity is way more important for dataset size. So we have like a lot of diverse content in there. We have a variety of object and camera motion, both small and large. And we also include different camera movements that we stress test kind of all different disocclusion scenarios. And also we include cases where motion vectors are not correct, such as particle shadows. And this is to ensure that the model learns the correct motion vector optical flow decision criteria. And then we also have a dataset labeling and analysis function. So we break down kind of failures of our model by content type rather than relying on one average score. And we use those weak areas to decide what training data should be captured on our next iteration in order to make sure that the diversity of the training dataset is always improving and targeted towards improving accuracy in areas that we care about. So the goal is not just a big dataset, it's a dataset that repeatedly exposes the model to situations that actually kind of challenge the model and make the interpolation more difficult. And how do we evaluate NFRU? I touched on this at the start, but evaluating frame gen is not as simple as checking whether every pixel matches the captured middle frame. Multiple outputs can be plausible, and real motion may accelerate or change in between a real frame, whereas our NFRU solution assumes linear motion, so we always assume we're interpolating exactly to the halfway point. And so this means a slightly earlier or slightly later position in the actual ground truth can look completely natural in motion. However, if you're using a pixel-based image quality metric, they may heavily penalize your result. Because effectively you're creating this pixel shift in your predictions. And this is particularly noticeable in sequences where you've got rapid acceleration, where the ground truth is not aligned to the halfway point, but your interpolation is firing straight at the halfway point. And so we don't have one complete solution to this, but we have developed systems to ensure that we can work around this problem. So we use metrics to kind of find regressions and compare large test sets consistently, but subjective review kind of still decides whether an artifact is actually visible or distracting or not. And so we have automated image quality CI, which helps to kind of capture and track these regressions at scale and makes it very easy us to visualize and determine whether we think the issues are real or not real. So in summary, the numbers kind of guide the investigation, but the final judgment as to whether the generated sequence looks convincing or not is down to us. Cool, so now for the fun bit, and we can get to look at some results. So this video shows the input to NFRU at 30 FPS and the output at 60 FPS, taken from Neural Dawn. Both videos have been slowed to 25% in order to visualize the differences. And as you can see, NFRU does a pretty good job in this scenario. This rotation is quite challenging because the character is effectively disoccluding itself with itself, but NFRU is able to recover the interpolated frame quite well with minimal IQ artifacts here. So I just want to touch on a couple of challenging cases. One of the key challenges in NFRU is shadow tracking, or ensuring that you are using optical flow in places where it is better. And so you can see this was an old, one of our original models, and at this point we hadn't quite got it clicking, and our shadows were not tracking nicely. However, now through a combination of improving our training data set, better hints, and smaller algorithm tweaks, we have been able to teach the model to learn the correct thing, and it is able to robustly pick optical flow in the right places, and this leads to quite nice shadow resolution. So as you can see, this is the video of the previous frame. On the left is the input and on the right is the output, and you can see this squirrel's shadow is nicely tracking, and there's no kind of beating artifacts or flickering. And then this is an example that links back to the very beginning of the deck when we were talking about quite challenging cases. So under very fast motion, the motion vectors will reproject the shadow back towards the camera, and normally this is fine to resolve. But in the edges, some of the candidate frames will not contain any information due to disocclusion. And so this makes the network's decision even more complex, and if not resolved properly, can lead to the shadow creeping in only the outer bound regions, causing incorrect shadow selection. We spent a good chunk of time on this sequence trying to resolve it, and it was basically a combination of quite a few things to resolve this. Training data is always a big one, but also we adjusted our clamping behavior for candidate frames in the outer bounds to ensure that the model isn't biased by outer bound clamping behavior. And what does this actually look like? So again, input on the left 30 frames per second, output 60 frames per second on the right. And you can see that the shadow is kind of correctly staying in the right place. So that means that the algorithm is correctly selecting optical flow in these regions and motion vectors in other regions. And this produces a nice clean result here. So we're getting towards the back end now of this presentation, and so to finish I'll put together what we've learned, where the remaining work is, and the resources available if you want to explore NFRU yourself. So bringing this together, NFRU is about making frame interpolation practical on mobile. It helps to meet rising frame expectations while staying within a realistic mobile power budget, and delivers smoother motion without requiring the game to render every displayed frame. The approach combines a graphics and with learnt reconstruction, and the models, I'll go into this a little bit more in a moment, but the models, the model gym, SDKs and plugins are there to enable developers to evaluate and build on this technique. So the aim is that we want to give developers a practical route to smoother motion without paying the full cost of every displayed frame. The main thing to mention as well here is that this is still an active area of development for us, and there are a few places where we want to push this further. So our current focus is on working to reduce thin ghosting around moving characters. We notice small little artifacts here, and we also want to improve difficult double disocclusion regions. So the current algorithmic investigations to try to resolve this, and we're looking at improving the disocclusion mask. We have a trial in-painting approach to resolve the double disocclusions, and we have broader training data for challenging cases, and we want to do this all while remaining in the same budget as the currently released model. As well as us working on NFRU though, we would like to invite you to build with us. NFRU is now open, and so you can inspect the shaders and the network to understand how the algorithm works. You can use the model gym and the released resources to experiment with your own ideas, or retrain and improve the model for your own content. Additionally, the weights and the shaders are available on Hugging Face, and you can find the model gym on GitHub. But we'd like this to be something that developers and researchers can inspect, test and improve upon, and it's not just a big black box. And I hope today's presentation has helped reveal some of our approach, and maybe we can work together to find ways to improve on this. So resources, this is kind of a bit of a one-stop shop for all of the things that are available right now. You can evaluate NFRU, you can integrate it into your game engines using the Neural Graphics SDK or the Unreal Engine plugin. You can train the model, and finally I would advise you to have a look at the ARM neurotechnology overview. This is our kind of one-stop shop for all things neurotechnology at ARM. So yeah, please go have a look and dig in. Finally, acknowledgements. This has been a real effort across many people in the company, so I just want to say a big thank you to everyone's efforts working towards this, and also to mention that this is not everybody. This is just a few other people to highlight. And finally, come and play our game. So Neural Dawn will be available in fall 2026. This is a really fun game. I've had a go myself. It's engaging, and it really demonstrates our two technologies, which are Neural Frame Rate Upscaling and Neural Supersampling and Denoising, into a really cool and nice visual game. So yeah, please have a come and play when it is released. And that is all for me today. So thank you very much. I hope you found this informative and enjoy the rest of your day.